Work. A little bit of physics for you today. Well, we're going to take a calculus approach to the physics. Anybody remember work from physics? What is it? Force times change of distance. So you should be able to calculate the work for a constant force. For instance, lifting up an object. That would be the work. But that's not real exciting. That's real simple, in fact. We want to deal with this. What happens when the force changes? Force for our purpose is going to be weight. So we're going to talk about lifting objects. We're going to talk about moving heavy things from the ground up to that would mean lifting. We'll talk about things leaking, emptying containers, pumping water, pumping oil, all kinds of different things like that. But what's going to change is the force. So if you're lifting up a bucket, for instance, and the bucket is leaking, the further you lift up the bucket, the less the weight, less water there is in the bucket, and therefore the weight changes. So that's where we'll have to use some calculus. And of course, you should become a Jedi Master in the next 24 hours. Already done? Good. Constant force, we'll do this one quickly. Force is, work is force times distance. How much force did you apply over how far did it move? So we'll look at a simple equation here, which is, we'll get to that in a second. But again, this is the big thing for us. In this class, we're going to consider weight to be the force that we're going to work with. We're not going to deal with like billiard balls colliding or trains running into walls and that kind of stuff. We're just going to deal with weight. Okay? So, simple thing. How much work is done to lift a 50-pound object 4 feet in the air? 200. Done. Any problems with that? Force, which is the weight, times the distance. What are my units? No.
Pounds times
What? Say it again.
pounds times feet. I don't know.
Good. Also known as foot-pounds.
Oh.
Again, how do you figure out the units? Well, what did we do? We multiplied pounds times feet. So what are our units? Foot-pounds. Anything different? Well, I don't know why that's so funny, but foot-pounds.
Is it real? Did you make that up?
Okay, so hold on. You're suggesting that I'm teaching you this and just teaching you incorrect information. This is not freshman geometry. Okay? In freshman geometry, they think they're called chords, not chords. They also think they're isosceles triangles. But there are actual units called foot-pounds. But you think I made that up? I didn't. Okay. What happens if the force changes? Little worksheet for you to follow along. That way you don't have to write so much. We're going to start by talking about some springs. What happens when you stretch a spring? Correct. And we're going to talk a little bit about Mr. Hook.
Captain.
So Mr. Hook was a guy that worked with springs. So this is the general concept we're going to use. We're going to calculate our force times distance. We're still going to stay with that same idea. Excuse me, but we're going to calculate how much force is done over a small distance, which we'll call dx. By now you should be comfortable with that idea that if we're talking about a small unit, we call it dx or dy or whatever it is we're dealing with. And then if we accumulate all those little pieces of work, then we get the final value for that total work done. How do we accumulate things? Integrals. So we get that. Where f of x is the force, also known as the weight, depending on the problem, and dx is the distance that it moves. Then we integrate it from a to b, from the starting point to the ending point, and lo and behold, we get the work. There are different ways to handle each of the work problems. So for instance, the way that we deal with springs in the first example is going to be different than the way we deal with lifting a weight in the second example, which will be different than the way we deal with emptying a cone in the third example, which will be different than the leaky bucket at the last example. Okay. So Robert Hooke, that's what he looked like, good looking guy. He did everything with springs, and he came up with that value for spring. So the force for a spring is K times X, where K is what's called the spring constant, and X is the distance that you stretch it. So all springs, if you just have a spring sitting there, has what's called a natural length. When you stretch that spring, then it starts to generate force. Depending on the spring that you're talking about, let's say it's a spring in your watch, for instance, versus a spring on your garage door, they're going to have a different spring constant, depending on how rigid or how weak the spring is. So when we're solving a problem, the first thing we need to do, if it's not given to you, is we need to find the spring constant. So here's our first example. We have a spring that takes 12 pounds of force to stretch it from its neutral position at 8 inches. In other words, the spring starts being 8 inches long. We take that 8-inch spring and we stretch it down to 11 inches. How far have we moved the spring? 3. Good, that's important. Not 11. It starts at 8, goes to 11. That's 3 units. We want to then use that information to solve these two problems. How much work is done to stretch it from 8 to 13, and how much work is done stretching it from 10 to 13? Which of those two answers would be bigger? A, because you're moving at a greater distance. The chunk of information we're missing in this problem, however, is the spring constant. So we have to find that first. So using the force equals K times X, I know from the first sentence that it took 12 pounds of force to stretch the spring 3 inches, which means that 12 is equal to 3K, sorry, and therefore K is equal to 4. No calculus involved, it's just a simple application of Hooke's law. No matter what you do to the spring from that point on, it's always going to have this spring constant of 4. And so we can use that to figure out the other two questions. All right, everybody with me so far? Any questions? We're good? Okay, let's do 8 together then. How far is it going to take to stretch it from 8 to 13? Well, 8 is you got to think of 8 as like 0. That's our starting point. And how far is it going to move to go from 8 to 13? Well, that's going to be 5. So our limits of integration are going to be from 0 to 5. The big question is, what's our force here? What's our equation for the force of this particular spring?
20.
Nope. 4x, correct. Because according to Hooke's law, the force is K times X, and we know that K is equal to 4. So our function here is 4x. And how far are we stretching the spring? We're stretching it just a little bit, which is dx, so we get that integral. 4x is the force, dx is the distance, and we're taking distances from 0 to 5. Go ahead and solve that integral. It's good for you. It builds character. I'm sorry, Kendrick, there's nothing to multiply out. You be okay?
Yeah, I'll be alright.
Don't forget units. Okay, most people in the first two rows got the correct answer. The tricky part is the units. What are the units on this problem?
Inch pounds.
Inch pounds, correct. Which again sounds funny, like I made it up. And as far as you know, I did not. What changes in the second part of the problem? Did the function change? Nope, same spring.
2 to 5 is neutral.
Right, we go from 2 to 5 now. So 10 to 13. If 8 is our neutral, we're starting at 10, which is 2, and we're going to 5. And so when you do that, you get 42 inch-pounds. Pregunta?
Yeah.
See?
How come we can't use like the first equation that you gave us? Why do we have to do this?
The only thing the first equation does for us is tells us what that K value is for the spring.
No, the like work equals force times distance.
Oh, we are using that. because the force, or the work, force times distance, is only for a little piece of this spring. And we want to integrate it over the entire distance.
Wait, so then why is it?
Hold on, let me think about stretching a string. You got, or I keep saying string, a spring. If you start to pull on a string, if I say string from now on, I mean spring. If you start pulling on a spring, to the right, it's going to be easier to pull at the beginning, but then when you get down to the bottom, it's going to be more difficult to pull, right? That's why it's a variable force. Whereas if I pick up a 50-pound weight, it's going to be 50 pounds at the ground, it's going to be 50 pounds up here, nothing changes. So that's just a straight work calculation. But with the spring, it changes over distance, and therefore you have to integrate it because each distance that you stretch the spring is going to have a different work amount. Does that make sense?
Yeah, so
Okay.
is it like the distance always gonna be X?
I hesitate to use always, but for the most part, yes.
Where'd you get x equals 5?
13. 8 is our neutral position, so to end at 13, we're going from 8 to 13.
Oh, it says 11 on the sheet.
No, that's our ending point for the first part of the problem. 8 to 11 is what we use to find the K value. Yeah?
Yeah.
Okay. We good? Any questions? First type of problem, so springs. Second type, more interesting. I've got an 800-pound beam. I don't know why I have an 800-pound beam, but I do. And it's hanging over the side of a building and I want to lift it up on top. The reason this becomes a variable force problem is because the weight of this cable changes as you pull the beam in. Initially, I start with how much weight on the cable. How much does the cable weigh? Thank you, 150 pounds. As I pull in some of the cable, the weight of the cable will reduce. This never changes. The weight of the object is always 800. That's easy. We need to figure out a way to represent the weight of that cable. And it says this already on your sheet. I did a little bit of a calculation there. If I have a 50-foot cable that weighs 150 pounds, then it weighs 3 pounds per foot. Does that make sense? Okay. So if I have 100, if at the start of the problem, if I pull in 1 foot of cable, how much does the cable now weigh?
147.
147. If I pull in 10 feet of cable, how much does it now weigh? 120. So you get the idea. What if I pull in X feet of cable? How much does the cable weigh? Perfect. 150 minus 3x. That's the hard part. So now, what are our two weights? Because again, the problem involves just force and distance. So force is weight. So the one thing that doesn't change is the weight of this. So that's 800 plus the weight of the cable. And you just told me the weight of the cable is 140 minus 3x. Right?
Is it 150 minus 3?
Is that not what I said? Did I say something different?
It said 140.
Sorry, I don't know where that came from. I'm having a bad day. Nobody cares. Okay. So there's the weight of here's the weight of the situation. And now we need to integrate. From what to what?
Zero.
0 to
20.
20. Why 20?
Because you're lifting the base.
Yeah, because it says in the problem that we're lifting the beam 20 feet, which leads us to that. So again, this is the weight of the object. That's the beam plus the cable. The dx is how far we moved it. We're just moving it a little bit. But we're taking those little bits and adding them up from 0 to 20. And just for practice, go ahead and solve that one. Without FN inting. One of the things that I always preach about is looking at the problem when you're done and seeing if your answer makes sense. That kind of breaks down, and you'll see when we solve this problem, you get an answer, and I have no idea if that answer makes sense or not. We will talk about, however, once we get this done, what answers won't make sense. Nice hat. And then don't forget units. All right, what do you got?
18,400 pounds.
Can somebody confirm?
Yeah.
Good. 18,400 foot-pounds. Does that answer make sense? I have no clue. I don't know what a foot, I wouldn't know a foot-pound if it bit me in the face. What answers would not make sense?
Negative.
Negative wouldn't make any sense.
If it was less than 800,
If it was less than 800, why?
because the weight itself is 800 and it's not going anywhere.
Okay. What else? 0. Very small value, like you said, less than 800. Okay. But even that, I mean, who knows what a foot-pound is? I have no clue. Okay, we good? Now let's talk about my favorite type, and these are filling containers, emptying containers, leaky containers, these kind of problems. This requires a different mindset. So we're going to start with a conical tank, and we're pumping the water out of that tank. So there's a couple of things in this problem that you notice. First of all, I told you the density of water. Is this something you need to know? Probably not. But you'll use it enough that you'll know that it's just 62.4 pounds per cubic foot. Why do I care about the density? Because my approach to this problem is I'm going to figure out the amount of work on a little sliver of water in that cone. So in order to find the work, I need to find the weight of that sliver of water and the distance that I'm going to move that sliver of water. If I can find that for that sliver of water, I can then integrate it for all the slivers of water that make up this conical tank. That'll be fun, right? Good. What shape is that sliver?
Cylinder.
It's a cylinder. Very good. How tall is that cylinder?
DX.
Beautiful. What's the volume of that cylinder?
Higher cube.
I'm sorry?
Higher cube.
Nope. Pi r squared. No, pi r round, cake r squared. That's the joke. I screwed it
Oh,
up.
higher squared times height.
Pi r squared, no. Pi r round, cake r squared.
Okay.
Get it now? Good. Back to the problem. What's the volume of this thing? I'm sorry.
Higher squared dx.
Pi r squared dx. But we don't want the volume, we want the weight. So for those of you that are scientific geniuses, geniuses, regardless, how do we find the weight given the density? Come on, you don't know that.
Mass over mass divided by volume.
I'm sorry, what?
Net density equals mass divided by volume.
Perfect. So the mass would be the volume times the density. Okay, so blah, 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 there we go. There's the weight of that sliver of water. The volume, which is pi r squared dx, that's the volume of a cylinder, times its density, which this one for water is 62.4. You will see problems where it's not water. It might be motor oil, it could be rocket fuel, it could be whatever else you want to, whatever other liquid you want to pump out of a cone, because I know you do a lot of that. Whatever it is, they'll have to give you the density. Click. Okay, so we take that. How far are we moving this sliver of water? Say again? Nope. Let me ask my question again. How far am I moving this sliver of water to get it out of the cone? X, correct. I defined it as X. Now, we're pumping, just so you're clear, we're pumping this water over the top of the cone. There are other problems where it leaks out of the bottom of the figure. Leaky bucket problem, we'll get to that later. This one, we're pumping it over the top. This isn't the only way to do the problem. I chose to define this distance as X, and if this is X, then this is going to be 20 minus X, because the problem tells us this is 20 high. You could do it the other way around. It doesn't matter. This one, in this case, happens to be a little bit easier. So I'm going to take that sliver of water, which weighs that much, and I'm going to move it that distance X. And work is force times distance. There's the force, there's the distance. And I'm integrating slivers of water from where to where? Beautiful, 0 to 20. The top of the tank is 0, bottom of the tank is 20. We're emptying the entire thing. Here's the weight, pi r squared dx 62.4. There's the distance x. And when I simplify it, I move the constants out in front because they don't matter. Just leave the 62.4 pi floating out in front there. I get pi r squared. That's bad because we have two variables there. How do we get rid of one of the variables? Wait, more importantly, let me ask this. Which variable are we going to get rid of? YR. This is important. Good. I heard somebody say dx. So dx tells you that that's the variable we're working with, not ours. How do I get rid of the r? Vinny?
Would it be 4 over r equals x over 20 minus x?
Close. Very close. 4 over r equals 20 over 20 minus x.
Okay.
Okay. Does anybody have any idea where that came from? Other than Vinny's brain?
I don't know.
We are using these similar triangles. So we've got the red triangle, which is 4, which is 4, which is 4. Or that. 4 by 20. And this triangle, America, it's supposed to be blue. Let's try that again. So it's not really America. There we go. Which is r and 20 minus x. So using some similar triangles there, Vinny did radius over radius equals height over height, which gets us to this guy. So I did all that in one big calculation. This is really bad mathematically because I'm working horizontally, forgive me. Set up that proportion, cross multiply, solve for r. Which is good, because now I can get rid of the r and put in something in terms of x. It doesn't make the problem any easier, in fact it complicates it quite a bit, but it does make it solvable now because we have but one variable. Okay? How did I go from here to here? Did that in my head? No, I FN'd it. It's too lazy to do it.
We could multiply it out.
We could multiply it out, shall we? You don't want to?
It's a lot of work.
Okay,
It's a Thursday, I'm not feeling it.
I understand. Can you all multiply that out? Do you know how to?
Yes.
Can anybody not? Don't be embarrassed. Okay. Square the binomial first, remembering, here, let me get this. Square the binomial first. Square the first term, multiply the two together, double it. 4 times 1/5 is 4/5, doubled is 8/5. Square the last term.
So you square the
Square the first, multiply them together, double them,
Double?
yeah, square the last. 4 times 1/5, 4/5 times 2, 8/5. Then I would distribute the x and get 16x minus 8/5 x squared plus 1/25 x cubed. Then take the integral from 0 to 20 with a 62.4 pi out in front. This is doable. Okay, nice easy binomials there. You know how to take, oh, sloppy. There we go. Bush league, sorry. Okay, and you get that. Again, I have no idea if that's a good answer or not. Sounds pretty impressive, but I have no clue. Okay, we're gonna stop there. We'll save the leaky bucket problem for first thing tomorrow. You should have enough information, however, to bang out most, if not all, of the day 112 homework problems. We get out at 30?
27.
Let's wait still. We'll save leaking bucket for tomorrow, because it requires some nasty calculations that we're gonna have to go slowly through. Okay?